So, in this lecture we are going to take recap. Many things probably have learned, but to build up the course we need to relook some of these aspects, otherwise we have to refer every time to book. Phase transformation materials has three important words. First one is obviously materials, which I assume you know, because world is full of materials. They are classified into three parts, mostly three parts, but they can be made in five. So, metal, ceramics and polymers. Polymers can have two things, two parts, one is elastomer, other one is the plastics. Similarly, you can also have composites or hybrids, but we are going to concentrate mostly on metals and ceramics, not on polymers. Second important thing is phase, and third is transformation. Transformation will be our main point of interest, but what is a phase? There is a lot of misnomer about phase in the literature. Some people say phase is nothing but a solid state of matter. Yes, if you consider very simplest way, it is nothing but another term for solid, liquid or gas. Like if I take ice in water, ice is solid H2O, water is liquid H2O. Similarly, vapor is gas H2O. Obviously, there is a distinct difference between gas and vapor. I am not going to clarify it now, but on a crude manner we can always consider these three things are present when you have a ice on a water in a confined environment. So, therefore, these three things are in thermodynamically stable condition if we know the pressure and temperature. Similarly, if I have soap bubbles, it is nothing but air inside the bubble, and what is a bubble? It is a liquid film. So, therefore, gas and liquid are in coexisting situation in a soap bubble, correct. But suppose if I have oil in water, both are liquid. So, if I consider oil and water both as a state of matter, liquid, then it should be single phase because they are liquid, unlike in the first case or the last case, but that is not the true. Whenever you have two liquids not miscible each other, we call them separate phase. This is very important thing we must remember. Whenever we have two liquids not miscible atomically, we call them separate phases. But what about, that is about this solid liquid. Gas, there is no distinction whether it is one gas or multiple gas, it is single phase, whereas air is consisting of so many different entities like oxygen, nitrogen, carbon dioxide, carbon monoxide, many more, moisture, argon, but they are considered as one gas. Mixture considers one gas, so one phase. We never distinguish between different components of the gas as separate phases. For the liquid, we distinguish liquids at different phase when they are not miscible. To give a simple example, if I take milk, add coffee into it or tea into it, the mixture is a single phase because coffee and milk will mix atomically. Similarly, if you mix tea with milk, it will mix completely. So, therefore, we call them not so separate phases but a single phase. But if I add two oils, one oil in water, then they are not miscible, they never will mix. That you can do the same simple experiments or you have done it in your school days. So, we call them separate phases. So, that is for the liquid, but what about the solid? Solid is the most complex stuff. Let us see, let us consider first the case of a metal, that is what we always give. Pure iron, iron is a God's gift, pure iron is a solid, okay, and it is consisting of only iron, okay. But if you look at from room temperature to melting temperature, iron melts at 1539 degrees Celsius temperature. It exists in three different crystal structures. Specifically, it exists in two different crystal structures, but we always consider it exists in three different crystal structures. What are they? At room temperature to 910 degrees Celsius temperature, that is what is shown here, that is what is shown here, I am sorry, okay. it is in body center cubic structure BCC. Okay. And once it goes to above 910 degrees Celsius temperature, it transforms to FCC. That is what we call gamma iron. Alpha becomes gamma, and this gamma iron remains stable till 1394 degrees Celsius temperature. Above 1394 degrees Celsius temperature, again it transforms to a BCC iron known as delta. Correct. So, you can see clearly a single solid, different phases exist in different crystal structure. So, the connecting phase in solid is the crystal structure. If I change the crystal structure, I change the phase, whether it is a pure or it is an alloy. So, that is what you must understand. So, the moment you change the crystal structure, you have making a new phase. In solid, the crystal structure dictates the phase. But what happens in the case of alloy? So, that is pure iron is still understandable. Remember, beta iron is nothing but a high pressure phase which is not shown in the 1 atmospheric pressure system. That is normal STP, we never show beta iron, but beta is sometimes people call beta, sometimes people call epsilon iron, but it is a high pressure phase. That is why beta is omitted here. Now, what about alloy? If we consider simple example steel, because iron is related to steel, a steel is nothing but iron carbon alloy. You add a little amount of iron, a little amount of carbon into iron to produce steel. But if you do that, you create a complex, so called complex microstructure which looks like a lamella consisting of many lamella. And if one does careful understanding of this, it is well known to everybody now that this is what is known as pearlite. It looks like a pearl, that is why it is called pearlite. It consisting of two phases, one is alpha iron solutions, it is almost pure alpha iron, carbon concentration is very low, other one is a compound Fe3C. So, immediately you see I can create a different chemical entity if I have an alloy by adding carbon into it. So, Fe3C, whether it has a different structure or not, because it has a different composition, it must be a separate phase. But here it very clear the Fe3C has autonomic crystal structure, it does not match with alpha beta gamma iron. So, by anyway it is also a different phase, but it need not be if it is a different chemical compositions, but even if it has similar crystal structure, it will be a separate phase, because it contains carbon, lot of carbon as compared to alpha iron. So, that it must be a separate phase. So, that is what you see in different phase diagrams. Like if you consider copper and silver, both are FCC structure, but the moment you mix them, they form eutectic copper and silver, both are solutions, both are FCC, but they have different chemistries. Both contain copper and silver, but they are different chemistries. So, therefore, crystal structure is one factor, other factor is the chemical composition that makes different phases. So, you will clearly see that is why the students always do mistake when they try to figure out whether it is phase or not a phase. So, these are the points you might understand. So, again I want to point it out to you, because these are the very basic concepts you should know. For a gas, it does not matter how many components are present in the gas mixture, it is always a single phase. Air is a single phase, or if you consider mixture between different gases of which is in cooking gas, methane or some other things, that is also a single phase. Liquid, if two liquids are miscible, we call it a single phase, if they are immiscible, we call it separate phases. Solid, two important factors which demarcate a phase, one is crystal structure, second was the composition. So, the pure metal there is no compositional change, so therefore crystal structure what dictates you the phases. Am I clear? So, that is what you must take away from these lectures. Now, to give an examples, I always teach this in the class. If I have sand and salt, are they separate phases? Yes, where sand and salt will never mix each other. Milk and coffee, single phase. If I mix milk in coffee, they will mix atomically. That is what gives you the taste. Coffee and sugar mixed completely. If I add sugar into coffee, stir it, it will mix. So, therefore, it is a single phase liquid. But if copy bins are used, the solid copy, and if you are adding sugar into it, they will not mix each other. So, therefore, they are two separate phases. Salt and water, no question needs to be asked because this is simple mixture. Okay, we call it brine and it is a single phase. Okay. So, you must be able to ask this question yourself and answer these questions, because phase is very important in the phase transformation or phase diagrams. Let us move on to the next thing. That is what I told you in this lecture, again reiterating. For solid, chemically and structurally distinct things are called phases. For liquid, miscibility dictates the phases, gas is always a single phase. So, phase is always a chemically homogeneous, physically distinct, mechanically separable portions of a system or a material is called a phase. Chemically homogeneous, why? Because it should have the same chemical composition. That is why chemical homogeneous. Physically distinct, it looks different. You can see under microscope or you can see by naked eye, it will look distinctly different from the other things. That is why in perlite one phase is in white contrast, other phase is in black contrast, they look different. And mechanically separate, we can separate them, like ice and water I can simply separate them, okay, but I cannot separate salt and water mixture. Salt and water cannot be separated mechanically, they are mixed atomically, that is why they cannot be separated atomically. Okay, so this definition is, many times is not understood properly, that is why you have to provide examples to make you clear. More discussion in my course. Now, transformations, the third important word. First of all, why phases will transform? That means they are not stable, that is why under certain condition, that is why they transform. Why ice transform to water? Because we know ice will melt above 0 degree Celsius temperature at normal atmospheric pressure. So, the moment you keep it in temperature condition more than 0 degree Celsius at 1 atmospheric pressure, it will melt down. But if you keep it at less than 0 degree Celsius temperature, it will not. So, there is something which makes them unstable, not stable actually, unstable is a very difficult word, they are not stable under certain experimental conditions, that is why they do get transformed. So, to understand that under what condition they will be stable or metastable or unstable, we must have an idea about equilibrium, because equilibrium is something which allows you to differentiate between these three important aspects. That is why I say concept of equilibrium is of fundamental importance, but nothing is at equilibrium in this world, everything is away from equilibrium, but still from the theoretical perspective we must know or must have an idea of equilibrium. Thermodynamic equilibrium is very important concepts. Thermodynamic equilibrium has three important aspects, because we are going to deal with thermodynamics. One is the mechanical equilibrium. What is mechanical equilibrium? We will discuss in the next slide. Second one is the thermal equilibrium. Thermal equilibrium means it is the conditions arising from absence of any temperature gradient. So, if I have a piece of metal or let us say piece of steel or piece of ceramic, there must not be existing any thermal gradients in anywhere in the sample. That means temperature has to be uniform, but making temperature uniform means the gradients to be 0. That is why you always define thermal equilibrium in terms of temperature, absence of temperature gradient in the material. Third important aspect for thermal equilibrium is the chemical equilibrium. Chemical equilibrium is obtained when no further reaction occurs between the reacting substance, that means forward and backward reactions rates are equal. Remember, you cannot stop reactions, but visually speaking you cannot say reaction is over or not unless and until you know the reaction rates of the forward reactions or the backward reaction are same. It is very simple. If I consider A plus B going to C, so this is the forward reaction, backward reaction is C going to A plus B. What it says is that the reaction rate of A plus B going to C must be same as C going to A plus B. The A plus B going to C is forward reaction, C going to A plus B is a backward reaction. So, when their rates are same, you will not see any changes happening in the system. and that is why you say chemical equilibrium. So, this is understandable. Thermal means there will be no temperature gradient, chemical means there will be no resultant reaction rates. The reaction rates, the forward or backward reactions will be same. What about chemical equilibrium, sorry, mechanical equilibrium? It is very easy to understand if I consider matchbox. Mechanical means energy, energy means kinetic plus potential energy. We know that in any material there will be atoms, atoms will be having both potential and the kinetic energies. So, when the energies of this system is at the minimum, both the energies together, then we call it mechanical equilibrium. If you consider a matchbox, matchbox has 6 faces, there are 2 broad faces and 4 short faces. If I keep the matchbox in one of the 2 broad faces on a plane, on a suppose table like this table, then it becomes, or it is better to show you this is exactly same as a matchbox. This is a duster. Duster has 2 flat faces, one this, other one is this. So, if I keep it like this, then on this table, or if I keep it like this, then we call it at equilibrium. Why? Because you can see that it is on the broad face, nothing will happen even if I do something, some force apply. Energy is at minimum, potential plus kinetic energy. But I can also keep it on one of these short faces like this, okay, or you can keep it like this, I do not know whether, yeah. See, it stands, but this is not at equilibrium, okay, global equilibrium. Why? Because if I apply a little force, it will fall back. Oh, it has gone inside, okay, does not matter, it will fall back, that is what it happens. Okay, so that is basically the problem with all these structures. Now, if I keep it like one of the edges and leave it, it will immediately fall. So, that is called unstable situation. You can see it is on the edge, it will not be standing even, it will fall. You can do all this experiment yourself, but if I keep it on this, it can still sit on it. I do not know whether this will sit, but it should be able to sit, yeah. But because height is longer, so obviously potential energy is higher, kinetic energy may be same, but potential energy is higher with respect to these plates than this configuration. So, therefore, this configuration is called equilibrium, this configuration is called metastable equilibrium, and this configuration is called unstable equilibrium. Okay? These are the 3 equilibrium, mechanical equilibrium concepts. So, in thermodynamic equilibrium, system has to be mechanical equilibrium, under mechanical equilibrium, under thermal equilibrium, under chemical equilibrium. When all the things are 3 things are satisfied, we call the system is at equilibrium. So, in phase transformation, you are taking away the system from the equilibrium, that is why it is transforming into something else. That is why equilibrium is the center point of discussions in all these things. Once you know very clearly that my system is at equilibrium under certain experimental condition, then you can be sure there will be no further phase transformations. But the equilibrium can be metastable or stable. Okay, that we will look into much later, because this is the very beginning of the lecture. Now, there is another important aspect I must tell you. Equilibrium can also be defined in terms of energy landscape. Energy landscape means energy of the system in terms of space. If I plot energy of the system like in terms of the space variable, space is x, y, z, you can consider one of these also, it will be okay. And suppose I have a well like this kind of well in energy versus coordinates or the distance diagram. Okay, so if I keep a ball here and drop it, it will simply fall and settle there, and it will not come out, because this is a well, it is a very deep well, energy well, and it has gone there. Similarly, if I keep a ball and set, it will fall back on the same positions, whatever I do. Even if I take this ball from this position and put it here, it will again fall back. So, that means system is at this position, system is at the global equilibrium. That means system is having lowest or minimum energy. Am I clear? Now, we can also have such a kind of local minima, okay, such a kind of things possible. So, if I drop a ball here, it should have fallen back here, but it is not. it is going and settling here, because there is a locally hump or locally some space to occupy this ball. Only when if I give a push like this, it will fall back to the goal. Once it fall back here, it cannot be again taken out there unless and until you simply apply force and put it there. So, this is what is known as metastable equilibrium. That means, in the way of moving, somewhere it finds a local equilibrium or local minima rather, and it got stuck there. That is what is known as metastable equilibrium. This is very important in steel, you will see it in details. Okay. That is what is known as metastable equilibrium. Now, what is unstable? Unstable equilibrium first. There are two things, unstable and unstable equilibrium. You must have a very good idea about that. Suppose an energy landscape is like this, inverted parabola, and if I put a ball here, it will simply fall this way or this way, it will not stay. This is what is this situation. It will either fall this way or fall this way, or if it is on the edges, correct. But still this is an equilibrium, because it is not dissipating any energy. But suppose if I have a path like this on a hill, let us imagine a situation, you are gone to the top of the hill and you are gliding on the hill. Basically it will simply glide down, and every time it glide down, it is dissipating energy. So, therefore, it is not an equilibrium. This is known as unstable or instable, whatever situation you can, unstable is better word. So, therefore, if system is dissipating energy, we cannot call it an equilibrium, whether stable, metastable or unstable. System must not dissipate energy to be in equilibrium conditions. It can be varying from stable, metastable or unstable, but the moment it dissipates energy, that means it is losing energy, then it is no longer in continually losing energy, basically that means no longer in equilibrium. So, this is something which you also understand. Okay, there will be many such situations where you want the system to be at global equilibrium, but system will not, it will try to remain in metastable equilibrium. Similarly, there will be situations where system is unstable equilibrium, immediately it will transform into two products. That is what is the third situation. Material worlds actually exactly same, these pictures. Okay, there are materials, if I simply change pressure and temperature conditions, they will be going into unstable equilibrium conditions, and immediately they will transform into some stable products. Similarly, there are materials which will not transform into the global equilibrium product or metastable equilibrium product and remain there peacefully for a long time. So, that is why this equilibrium concept is very important for you. Okay. So, I think we should stop here, and in the next lecture we will discuss in more details about these things.